Welcome to GATE class. Let us see the properties of Fourier transform. Properties of discrete time Fourier transform. So the first property is called the periodicity property. So according to this property, if we add 2 pi to ohm, then it is equals to x ohm only. So basically that period, it is periodic with period 2 pi only. So in case of discrete time signal, in case of discrete time, what we have considered the value of ohm. We have considered the value of ohm over the range 0 less than or equal to ohm less than or equal to 2 pi, or minus pi is less than or equal to ohm less than or equal to pi. So if we consider the continuous case, so while in continuous time case, we have to consider values of omega, that is in radians per second, over the range minus infinity is less than omega less than infinity. Let us see the linearity property. So we have a1 x1 n plus a2 x2 n. That discrete time Fourier transform is a1 x1 ohm plus a2 x2 ohm. This is called the linearity property. Then we have another very important property. This property is called the time. This property is called the time shifting property. So according to this property, xn minus n naught, if we find out the Fourier transform, it is equals to e raised to the power minus j ohm n naught into x ohm. Then we have frequency shifting property. According to this property, if we multiply e raised to the power j ohm naught n with x, then that is equals to x ohm minus ohm naught. This is called the frequency shifting property. Then we have conjugation property. So according to this property, x conjugate n, if we find out the discrete time Fourier transform, then it is equals to x conjugate minus ohm, where star denotes the complex conjugate. conjugate. Also, we have very important property. That property is called the time reversal property. That property is called the time reversal property. So according to this property, x minus n, if we find out the discrete time Fourier transform, then that is equal to x minus o. Then we have time scaling property. According to this property, if we scale the time, means if we find out that, just first let us discuss this by understanding what is the time scaling property in case of continuous time signal. So in case of continuous time signal, that xt is a continuous time signal, let xt is a continuous time signal, then xat, the Fourier transform of this is 1 divided by modulus of a x omega divided by a. Now if we consider, however, in the discrete time case, in the discrete time case, x an is not a sequence, if a is an integer. If a is an integer, then xan is not a sequence. On the other hand, if a is integer, say a is equals to 2, then x 2n consists of only the even samples of xn, Thus, time scaling in discrete time takes somewhat different form as compared to continuous case, and we express it as it is just simple. We have x and n, that is, it is written as x n by m is equals to xk if n is equals to km, and where k is an integer, and it is equals to 0 if n is equals to km, because if n is equals to km, then it is equals to 0. So that time scaling property, for this we can write it in this form. If we write it in this form, that is equals to xm. This is simply the time scaling property. So it states that again the inverse relationship between the time and frequency, that is, as the signal spreads in time, basically as the signal spreads in time, as the signal spreads in time. We say that for m greater than 1, the signal will spread in time. Its Fourier transform will compressed. Its Fourier transform will compressed. Its Fourier transform will compressed. So that important point is that this is very important point, that compression in time domain leads to expansion in frequency domain. And vice versa. It means if we have expansion in time domain, so we have this. If we have time domain and there is a frequency domain, so if we have expansion in time domain, then we have compression in frequency domain, and if we have compression in time domain, then we have expansion in frequency domain. So this is very important property. Let us see the next property, that is called the duality property. That is called the duality property. So according to this property, if we have Fourier transform so let us take the first consider the continuous time case. Then it is simply that 2 pi x minus omega. So if we have xt, that Fourier transform is x omega, then if we replace omega with t, so this is the case of continuous time signal. Just like if we consider the discrete time case, then what will happen, that if we have we have to consider the Fourier coefficient in terms of, we have to see in terms of Fourier coefficient. So basically there is no direct there is no discrete time counterpart for this property in case of discrete time signal. So there is no discrete time counterpart of this property. So what is happening, that however there is a duality, there is a duality between the discrete time Fourier transform and continuous time Fourier transform. So if we have xn, that is x ohm, then we have x ohm, that is equals to summation n is equals to minus infinity to plus infinity xn e raised to the power minus j ohm n. So x ohm plus 2 pi is equals to x ohm. So since ohm is a continuous variable, since ohm is a continuous variable, letting ohm is equals to t and n is equals to minus k, we have we have xt, that is equals to summation k is equals to minus infinity to plus infinity x of minus k e raised to the power jkt. Since xt is periodic with period 2 pi, with period t naught is equals to 2 pi, and the fundamental frequency omega naught is equals to 2 pi divided by t naught is equals to 1. So what we can find out that Fourier series coefficient, Fourier series coefficient of ext will be x of minus k, that is ext, the Fourier series coefficient is ck, that is equals to x of minus k, where fs denotes the Fourier series and ck is its Fourier coefficient, where fs denotes the Fourier series and ck are its Fourier coefficients, So let us discuss another property, that is called the differentiation in frequency. Differentiation in frequency. So according to this property, if we take nxn, then the differentiation is j d x ohm divided by d ohm. That is, another property is called the differencing. So xn minus 1, if we find out that, then 1 minus e raised to the power minus j ohm into x ohm. This is called the differencing property. So this xn minus 1, this is basically called the first difference sequence. First difference sequence. This is called the first difference sequence. So lastly we can see that there are some other properties that are very important, and not last, we have many more properties like this, but these properties are very important. So let us see another very important property, that is called the convolution property. Before that, let us discuss the accumulation property. So let us see the accumulation property. So if we consider that summation k is equals to minus infinity to n x k, that is equals to pi x0 into del ohm plus 1 divided by 1 minus e raised to the power minus j ohm into x ohm, and we have modulus of ohm over the range of pi. So this that note that this accumulation property in the discrete time counterpart of integration. So basically this is the integration discrete time counterpart of the integration. So the impulse term on the right hand side reflects the DC or average gain. This impulse term, so this is basically the DC or average gain. This is basically the DC or average gain. This is basically the DC or average gain. Results due to accumulation. Results due to accumulation. So next property is convolution. That is very important property. So if we have x1n convolution with x2n, then it is nothing but multiplication of x1 ohm with x2 ohm. So again we have if we have convolution in time domain, if we have convolution in discrete time domain, then we have multiplication in ohm domain. We have multiplication in frequency domain, that is ohm domain. So just like we have the case of Z transform also, this convolution properties plays an important role in the study of discrete time LTI system. So just like we have Z transform, here we have this Hn, then we have Xn, then we have Yn. So this discrete time LTI system, let us this is discrete time LTI system. So this Yn is equals to Xn convolution with Hn, then Y ohm is equals to X ohm convolution with H ohm. This Y ohm is equals to X ohm convolution with H ohm. So this is very important property. Next property is called the multiplication property. Next property is called the multiplication property. This property is very important. What is the property? Is telling that if we have x1n multiplied with x2n, then it is equals to 1 divided by 2 pi x1 ohm convolution with x2 ohm. So what is that x1 ohm convolution with x2 ohm, and that is equals to x1 theta multiplied by x2 ohm minus theta d theta. So this property is called the multiplication property. So we have multiplication in time domain is equals to convolution in ohm domain. This property is telling that the multiplication in time domain is equals to convolution in ohm domain. There are some additional properties. So if xn is real, what is that additional property? If xn is real, then xn is equals to xen plus xon, that is even and odd part component of xn. Then xo is equals to x e ohm, that is equals to basically we have, it can be written as xe ohm plus jxo ohm. So what is xe ohm? That is equals to real part of x ohm, and let us denote it as a ohm. So it is equals to a ohm plus jb ohm, and xo n is equals to imaginary part. So basically it is It is j into imaginary part of x ohm, and this is equals to b ohm. So a very important thing is a minus ohm is equals to a ohm, and b minus ohm is equals to minus of b ohm. Please understand that. This is very important. And modulus of x minus ohm is equal to modulus of x ohm, and theta of minus ohm is equal to minus theta of ohm. So if xn is real and even, so very important property comes from that. If xn is real and even, if xn is real and even, then x ohm is real and even, real and even, real and the property is that if xn is real and even, then x ohm is real and even, while if xn is real and odd, while if xn is real and odd, then x ohm is imaginary and odd. Then x ohm is imaginary and odd. Next property is called the Parseval's relation. So according to this property, summation n is equals to minus infinity to plus infinity x1 n multiplied by x2 n is equals to 1 divided by 2 pi x1 ohm x2 minus ohm d ohm. So we can write it as summation n is equals to minus infinity to plus infinity modulus of xn whole square is equals to 1 divided by 2 pi integration of 2 pi x ohm square d ohm. So this is known as Parseval's identity. This is known as Parseval's identity or Parseval's theorem. This is known as Parseval's identity or Parseval's theorem. This is known as Parseval's identity or Parseval's theorem. Let us discuss the frequency response of discrete time LTI system. Let us discuss the frequency response of discrete time LTI system. So let us discuss the frequency response. So if output yn is the output of discrete time, that we have defined that if yn is output, then it is related to xn convolution with hn. Then we have defined. So taking Fourier transform on both sides, ym is equals to x ohm multiplied by h ohm. So finally what we are getting here, that h ohm is equals to y ohm divided by x ohm. That is called a transfer function. That is called a transfer function. That is called a transfer function. So also this h ohm can be written as modulus of h ohm. This h ohm can be written as modulus of h ohm e raised to the power j theta h ohm. So what is that h ohm? It is called the frequency response of the system or the transfer functions, and then modulus of h ohm is called the magnitude response of the system. Magnitude response of the system, and this theta h ohm is called the phase response of the system. Theta h ohm is called the phase response of the system. Theta h ohm is called the phase response of the system. Modulus of h ohm is called the magnitude response of the system. So we have Hn and we have H ohm. Then we have del n and xn. So we have x ohm here. We have Hn. If we are giving the input as del n, then the output is impulse response, and if we are giving xn, then yn is equals to xn convolution with hn, that is equals to y ohm is equals to x ohm into h ohm. That is y ohm is equal to x ohm into h ohm. So consider the complex exponential sequence. Consider the complex exponential sequence xn is equals to e raised to the power j ohm naught n. Now let us set thus setting z is equals to e raised to the power j ohm naught n. What we are getting yn is equals to h e raised to the power j ohm naught e raised to the power j ohm naught n, and that is equals to h ohm naught e raised to the power j ohm naught into n. So which indicates that the complex exponential sequence e raised to the power j ohm naught n is an eigenfunction of the LTI system. So it indicates that it indicates that the complex exponential sequence e raised to the power j ohm naught n is an eigenfunction of LTI system which with corresponding eigenvalue h ohm naught. So furthermore, we can see that if we have discrete time counterpart, that if we have xn, that is equals to summation k ck e raised to the power jk ohm naught n, and ohm naught is equals to 2 pi divided by n naught. Then what is yn? What is yn? Yn is equals to summation k is equals to n naught, that is range over n ck h k ohm naught e raised to the power jk ohm naught into n. So if xn is not periodic, then yn can be written as, so and also if xn is not periodic, then yn can be written as 1 divided by 2 pi integration 2 pi h ohm x ohm e raised to the power j ohm n into d ohm. So this is the relation. Now LTI, let us consider the LTI system characterized by difference equation. LTI system, let us discuss the LTI system characterized by differential equation. So summation k is equals to 0 to capital N a k y n minus k, it is equals to summation k is equals to 0 to capital M b k x n minus k. This is the equation. This is the difference equation. So with m less than or equal to n, that we all know. So what we can find out, that we can find out the Fourier transform on both sides. So what we can find out, we can write it as k is equals to 0 to capital N a k e raised to the power minus j k ohm into y ohm, that is equals to summation k is equals to 0 to capital M b k e raised to the power minus j k ohm into x ohm. So what we can write finally is h ohm, that is equals to y ohm divided by x ohm, and it is equals to summation k is equals to 0 to capital M b k e raised to the power minus j k ohm divided by summation k is equals to 0 to capital N a k e raised to the power minus j k ohm. So h ohm is equals to hz when we have z is equals to e raised to the power j ohm, that is equals to h e raised to the power j ohm. Let us see the periodic nature of frequency response. Let us see the periodic nature of frequency response. So periodic nature of frequency response is h ohm should be equal to h ohm plus 2 pi. So unlikely the frequency response of continuous time system, that all of discrete time LTI system is periodic with period 2 pi, but here we need to observe the frequency response of a system over only the frequency range 0 to 2 pi or minus pi to 2 pi. That's why we have taken this relationship h ohm is equal to h ohm plus 2 pi. So let us see the system response to sampled continuous time sinusoids. System response to sampled continuous time sinusoids. So let us see the system responses. Let us see the system responses. So let us denote that YCN, YSN and YN are the system responses to cos ohm and psi ohm and e raised to the power j ohm n respectively. So we denote by YCN, YSN and YN the system responses to cos ohm n, sin ohm n and e raised to the power j ohm n respectively. Since e raised to the power j ohm n is equals to cos ohm n plus j sin ohm n, it follows the linearity property of the system that linearity property of the system that yn is equals to ycn plus jysn, and that is equals to h ohm e raised to the power j ohm n, and ycn is equals to real part of yn, that is also the real part of h ohm e raised to the power j ohm n. Let us see that. And ys on sn is imaginary part of yn, and that is also imaginary part of h ohm e raised to the power j ohm n. So if we just draw the diagram, then it will be clear. So we have h ohm, that is system e raised to the power j ohm n. The output yn is equals to h ohm e raised to the power j ohm n, then cos ohm n, sin ohm n, we get ycn, that is equals to real part of h ohm e raised to the power j ohm n, ysn is imaginary part of h ohm e raised to the power j ohm n. So when a sinusoid cos ohm n when a sinusoid cos ohm n is obtained by sampling, when a sinusoid cos ohm n is obtained by sampling a continuous time sinusoid cos omega t with sampling interval ts, that is cos ohm n is equals to cos omega t when t is equals to nts, that is equals to cos omega ts into n, that is cos omega ts into n. All the results developed in this section apply if we substitute omega ts for ohm, that is ohm is equals to omega ts. So what is happening that for a continuous time sinusoid cos omega t, there is a unique waveform for every value of omega in the range 0 to infinity. So it is very interesting to see that omega results in a sinusoid of ever increasing frequency. On the other hand, the discrete time sinusoid cos omega n has a unique waveform only for the value of ohm in the range from 0 to 2 pi or minus pi to pi. So it is very interesting to note that cos ohm plus 2m pi multiplied by m, that is periodic, it is equals to cos ohm n plus 2 pi mn, and that is equals to cos ohm n if m is an integer. So further we can say that if we have cos ohm pi plus minus ohm into n, then it is equals to cos pi n cos ohm n minus plus sin pi n sin ohm n, so that is equals to minus 1 raised to the power n cos ohm n. So what we can observe that cos pi plus ohm into n, that is equals to cos pi minus ohm into n. So cos pi plus ohm into n is equals to cos pi minus ohm into n. So this equation tells that A sinusoid of frequency pi plus ohm has the same waveform as one with the frequency pi minus ohm. Therefore, a sinusoid with any value of ohm outside the range 0 to 2 pi is identical to a sinusoid with ohm in the range of 0 to pi. Thus, we conclude that every discrete time sinusoid with a with a frequency in the range 0 is less than ohm less than pi has a distinct waveform, and we need to observe only the frequency response of a system over the frequency range 0 to pi. Let us denote another very important term, that is called the sampling rate. That is called the sampling rate. So what is that mean? If omega m is 2 pi fm, is the highest frequency component, is the highest frequency component, then if the highest frequency component of the continuous time signal, then what is that meaning is omega m ts should be less than pi, or ts should be less than pi divided by omega n. And what is that? Fs is greater than 2 fm, or it can also be written as Fs is greater than 2 fm. So this is called the sampling. This is called the sampling rate. So Fs is called the Fs is equal to 1 divided by Ts is called the sampling rate. It is called the sampling rate. Fs is equal to 1 divided by Ts is called the sampling rate. So this is also called the sampling theorem. So this is very important when if we are taking greater than 2 fm, then it is good to reconstruct the signal at the receiver. When we have Fs less than 2 fm, then we are getting the overlapping, so it is very difficult to extract the signal at the receiver. It is very difficult to extract the signal at the receiver when we are doing sampling less than the sampling rate. So let us discuss another very important term, that is called the discrete Fourier transform. Discrete Fourier transform, that is called the DFT. That is called the DFT. So this DFT is basically it is for finite length sequence. This DFT is for finite length sequence. Finite length sequence. We are considering the DFT, that is discrete Fourier transform, for finite length sequence. And also that please understand that DFT and Fourier transform are different terms. So please do not confuse DFT with Fourier transform, that is discrete time Fourier transform. So let us see what is the definition of that. So let Xn be a finite length sequence. Let Xn be a finite length sequence of length n, that is Xn is equal to 0 outside the range 0 is less than or equal to n less than or equal to capital N minus 1. So the DFT of Xn, denoted as xk is defined by is defined by xk is equals to summation k is equal summation n is equals to 0 to capital N minus 1 xn wn raised to the power kn, where k is equals to 0, 1, 2 up to capital N minus 1. And what is wn? So wn is known as the nth root of unity. Wn is known as the nth root of unity, and wn is written as e raised to the power minus j 2 pi divided by capital N, and that xn is equals to 1 divided by capital N summation n is equals to 0 to capital N minus 1 xk wn raised to the power minus kn, where n is equals to 0, 1, 2 up to capital N minus 1. So the DFT pair is denoted as, we have xn, the DFT pair is denoted as, the DFT of xn is xk. This is the DFT pair. This is the DFT pair. This is the DFT pair. So what are the important points of DFT? Let us discuss the important point of DFT. The important points of DFT. So the important point of DFT is there is a one-to-one correspondence between xn and xk. There is a one-to-one correspondence between xn and exk. The second important point is that there is an extremely fast algorithm called the FFT for its calculation. So we are using fast Fourier transform. We are using fast Fourier transform because it is very efficient algorithm for computing the discrete Fourier transform. So please understand that for implementation purpose we are using FFT because it is very fast as compared to DFT. Also the DFT is closely related to DT, discrete Fourier series, and Fourier transform. So DFT is closely related to Fourier transform and discrete Fourier series. So it is closely related to Fourier transform and discrete Fourier series. Also the DFT is an appropriate Fourier representation of digital computer realization because it is discrete and of finite length in both the time and frequency domain. So the DFT is appropriate Fourier representation Fourier representation for digital computer realization, for digital computer realization because in discrete because it is discrete because it is discrete and of finite length in both the time and frequency domains. In both the time and frequency domains. In both the time and frequency domains. So please note that the choice of capital N is not fixed. If xn has a length n1 less than n, we want to assume that xn has a length capital N by simply adding n minus n1 samples with a value of 0. Okay, so this is called the dummy zero padding. This is called the dummy sample and it is called the zero padding. So thus the resultant xn is often referred to as the endpoint sequence. Okay, so basically we are computing the DFT for a finite length sequence, that is endpoint sequence. So it is also denoted by, so it is called the endpoint DFT. Endpoint DFT. This is also denoted as endpoint DFT. So let us see the relationship between the DFT and the discrete Fourier series. So the relation between DFT and discrete Fourier series. Let us see the relation. So the relation is xk is equals to capital N times ck. This is the relation between DFT and discrete Fourier series. Also we can find out the relation between DFT and Fourier transform. So what is the relation? So xom is equals to summation n is equals to 0 to capital N minus 1 xn e raised to the power minus j ohm n. Then what we can see that xk is equals to x ohm. We have ohm is equals to k 2 pi divided by capital N, and that is equals to x 2 pi k divided by capital N. This is the relation. So thus xk corresponds to sample x ohm is the uniformly spaced frequency. So what we can see that thus xk corresponds to x ohm is the uniformly spaced frequencies ohm is equals to 2 pi small k divided by capital N for k has some integer value. For k, that is some integer value. So if we have x ohm, then replacing ohm with 2 pi small k divided by capital N will give us xk.